So in this particular problem, it asks us what the acceleration of the system is, the magnitude of the tensions, and we're going to assume that the surface is frictionless and the pulley has a rotational inertia of a uniform disk. We're given M1, M2, the mass of the pulley, the radius of the pulley, and the angle of incline theta, and we use any physical constants like the acceleration due to gravity g. We're going to use our complete second law toolkit. Now we're adding the fact that the sum of the torques equals I alpha. So we're going to start off using the system technique, or looking at the entire system of mass M1 and M2 and the mass of the string. We're going to call counterclockwise along the string positive. This is what we call the magic pulley technique. Okay, so I'm going to refer to this green line later on. So everything along the direction of this green line counterclockwise is going to be positive. The motion maps show that M1 is moving up and to the left, accelerating up and to the left, and M2 is accelerating downward. The force diagrams, if I take M2 and I move it over here and just look at its force diagram, FG2 is going to be downward, FT2 is upward. M1 will have normal force up and to the right, the force of tension T1 up and to the left, and the force due to gravity FG1 downward. Rotating if necessary, so M1 would be one that we can rotate if we'd like. However, I think what we'll do is we're a little more advanced, so we'll look at M1 just as it is on the incline itself without really having to rotate it. Step 4 is for our system to say the sum of the forces equals the mass times acceleration. We're explicitly writing out the sum of the forces equals the mass times acceleration. If we look at our system here, so along this green line, FG2 is going to be positive. FT2 upward is going to be negative. FT1 along the green line is going to be positive, and FG1x is going to be negative. Now, FG1x is still along the direction of this green line, but in the opposite direction. Because it's the entire system, we're going to include M1 and M2 and multiply that times acceleration. So this is Newton's second law filled in for our system along the green line. Okay, now we're going to look at each object. So we were using the system technique for M1 and M2. Now we're going to look at specifically each object. So M1, we're going to say to the left is positive, or along the incline up and to the left is positive, with the normal force up, FT1 to the left, and the components of FG1, FG1y down, and FG1x to the right. Step 4 for each object is to write out Newton's second law. Now for M1, there's a horizontal and vertical components for it. In the vertical, we've got Fn, which is going to be positive, minus Fg1y, which is downward. So that's just in the vertical. We know there's no acceleration vertically. We didn't even bother drawing a motion map in the vertical. So we know that the sum of the forces vertically is going to be 0. In the horizontal, though, we're calling to the left positive, so Ft1y is going to be positive, minus Fg1x, which is right there, that's going to be negative. They're going to equal some net force, M1 times AX. Okay, so there's going to be some net horizontal force of Ft1. If we look at M2, we're not going to bother with a horizontal equation because there are no horizontal forces, so we'll just look at the vertical. Now, I'm going to refer back to that green line that I talked about before. That green line showed that downward is going to be positive, so we'll call FG2 positive and FT2 negative. Okay, there's going to be a net force there as well, so that's going to be M2y. Now let's look at the mass of the pulley. So if we look at the mass of the pulley on its own, and we look at its force diagram, we're going to say that the sum of the torques equals I alpha. These three forces, the normal force horizontally and the normal force vertically on the pulley, along with the force due to gravity, are all going to have zero torques because all of their forces are applied at the axis of rotation. So when we use the equation for the torque for any of these forces of R times F, they're all going to have R's of 0. So they're going to, all three of these forces have zero torques. Now Ft1 and Ft2 will not have zero torques because their forces are not being applied at the axis of rotation. As a matter of fact, they're applied a distance r sub p away from the axis of rotation. So there are going to be two non-zero torques. They come from Ft1 and Ft2. If we look at Ft2, that's going in the counterclockwise direction. That we're calling that direction positive. So its torque is going to be Rp times Ft2. Okay. Likewise for Ft1, it's also going to have a torque, but it's going to be negative Rp times Ft1. According to the rotational version of Newton's second law, that's going to equal I alpha. So these are the three equations for each individual object. Okay, now that we looked at the system equation, which is that equation there, and we've looked at each individual mass, we've got 1, 2, 3, 4, 5 equations. So it's our job now to figure out which one of those 5 equations will help us find the acceleration of the system. So obviously we're going to use this equation, the acceleration equation, in combination with one of the other two equations. And what we'll find out after we do plenty of these is that we're going to start off with this equation there, that equation that I highlighted in red, and the system equation, and we're going to combine those two equations to help find the acceleration. So we got to do some algebra here. So there's a system equation, the linear system equation, and here's a rotational equation. So for our rotational equation, we'll start with that first. It told us it's a disk, so the disk's inertia is calculated out as 1/2 mr squared. Using the variables that given to us, we're going to use the mass of the pulley as m sub p and the radius of the pulley as r sub p. Then we'll take that equation for the rotational inertia of the disk, plug it back into our original equation so that we get this new equation here. Okay, then we'll factor out our r sub p on the left-hand side, and then divide both sides by r sub p, and that's what we would end up with. And then use our bridge equation, a is equal to r alpha, or the tangential acceleration is equal to r alpha. So using our variables, we're going to use r sub p. Let's plug r sub p alpha back into this equation so that now our equation is written out like this. What I'm going to do is I'm going to multiply both sides by -1, because what that will do is that'll help us plug this equation into that equation there. So notice that this part of the equation, because we multiply both sides by -1, looks like that part of the equation. So I'm going to do some substitution where I plug this part of the equation into that equation. So essentially -1/2 MPa I'm going to put into there. That's going to replace Ft2 and Ft1. So now I'm going to do some math, or I'm going to plug in some values. I know that Fg2 is equal to M2g because, so I know that that's how we calculate the weight of M2g. We plug that into there. Fg1x is this component, or the sine component of Fg1, so Fg1x will be m1g sine theta, so I'm going to plug that into there. So both of those equations plug into that equation, so that now this becomes my system equation. What I'll do now is I will bring over the 1/2 MPa. I'm going to add that over to the other side. So over here, I'm going to collect like terms, factor out the a. So this is what I get on the right-hand side. I divide both sides by a, so I get this. Okay, ignore this dotted red line here. Okay, so now this is my acceleration for my system, but it's also the acceleration for each object, for M1, M2, And what I can do now is I can use one of my equations to solve for Ft1. So now I'm going to combine this acceleration with one of my other equations, specifically this equation because it has Ft1 in it. So I'm going to plug in that acceleration into that acceleration because, again, we said that this system acceleration is going to be the same as that acceleration for mass m1. So if we plug that in, I know that fg1x, again, is m1g sine theta. So if I rewrite this equation to reflect m1g sine theta, what I then do is I add the m1g sine theta over on the other side, and I plug this acceleration into that acceleration to get this equation. So this is my equation for the total force of tension on T1. Then I've got to do the same thing for Ft2. So this is my equation for F that includes Ft2. I'm going to have to plug this equation, the acceleration equation, into that equation as well. I know that Fg2, we were calling that the positive direction, Ft2 upwards as the negative direction. So Fg2 is equal to m2g. That's how we calculate out the force due to gravity. Okay, so I plug that into that equation. That becomes that equation. Then I'm going to add the I'm going to subtract m2g from both sides. So this is what I now get. I want this equation written out so that it's positive. So I'm going to multiply both sides by -1. So now I got Ft2 is equal to negative m2a plus f2g. But remember, we said that acceleration there is going to be the same as that acceleration. So we just plug that equation into there to get this equation for the force of tension Ft2. And that's it.